And so I would like to welcome and thank you, Steve Wright, for agreeing to give us this talk. And I think it's very interesting, this idea of having multiple audience over there and here at the same time. He's from the Magnetic Resonance System Laboratory, the Department of Electrical and Computer Engineering from Texas A&M University. I met him a long time ago, and I was able to visit his lab, which is very interesting, and see how the students build their own scanner. So with that, thank you, Steve, and it's your stage.
Okay, thank you, Pablo. I really appreciate the opportunity to speak to all of you, particularly about desktop scanning, which is a topic that's of real interest to us. What I'll do is I'll give you a quick intro about Texas A&M and our lab, talk about why we're interested in hardware, because it turns out that the hardware is still important. Then I'll talk about our desktop scanning, and what we're doing is the class that is here is actually building and testing out this scanner for the first time. We've changed the course to a new platform, and looking forward to an interesting semester. Then if there's time left, I'll talk about some brief other hardware projects that have to do with, simplifying hardware. So let me go quick intro. So for those of you who don't know, Texas A&M is obviously in Texas, and we're actually situated conveniently sort of in the middle of all the 4 major metropolitan areas in Texas. So it's a good place to be from, because you can get anywhere from here, heart of Texas. Texas A&M actually opened as a military school in 1876, didn't open to civilians until the mid-60s. Now we have over 73,000 students, depending on, if you include all the campuses, which they say is the largest in the United States. The showpiece for the engineering college is this Zachary Engineering Complex, which we're in right now, opened a few years ago, 525,000 square feet dedicated purely to undergrad and grad education, which makes it the largest single educational building, I'm told, in the country. It's got an open labs concept, and that's the picture here, where all of our labs now take place in this building.
Sorry, Steve, are you projecting something other than the outline?
Yes, I am. Did that not work?
No, we are seeing only the outline.
Okay, let me try sharing a different screen here. Thank you. How about this one? Do you see the Zachary building now?
Oh yeah. Now we see a much more interesting slide.
Okay. I should go back and show Texas again, but you know where Texas is. So this is our engineering complex, and this is our shared labs. So all of our MR courses are in that lab, or at least this course is, which allows the students to go in and ideally work whenever they want. Doesn't quite work that way. Our research lab is pictured here. We have a number of magnets, 2 4.7 Tesla superconducting magnets, one of which we just shut down in anticipation of getting a new 7T magnet. We have a extremity scanner, and then that's actually interfaced to a homemade scanner that we'll talk about if there's time here. And like I said, we're getting a 7T MR solution scanner hopefully soon. We do a lot of courses. We have ECN 411, which is where the students actually use our desktop or our clinical scanner, small animal clinical scanner. This course where they build their own MRI, and then some graduate courses that are related. In this course, students actually build a scanner and make images, and this is the first phase encoded image off of that, and we'll talk about that a little bit more. So let me talk about just some motivation, why we still do hardware. Our lab has always been hardware oriented, and bringing students up to speed with RF and analog design is an important challenge. So we look for good ways to do that. Hardware, in my opinion, is often the choke point for innovation. I mean, if you think about it, there's an idea. Sometimes, Nobel-worthy ideas, we'll talk about one in a moment. Then you have to implement it, and the implementation often waits for hardware. ideas are there, but if you can't do it, and then of course the hard part, translating it, and that's, you know, we tend to be in stage 2. The heavy lifting goes on in stage 3. Let's consider a few examples. So, for those of you familiar with MRI, Peter Mansfield, who shared the Nobel Prize for MRI, his original conception of MRI involved echoplanar imaging. And, you know, he wrote a paper and said that if basically his analysis shows that if we could rapidly vary gradients, we could do extremely fast imaging. It took many years for that to happen, simply because the hardware wasn't up to it. We did not have the gradient systems that would produce these rapidly varying systems. Another example that I love, back when I started in this business, we had 0.5 Tesla magnets, and General Electric came out or said they were going to come out with a 1.5 Tesla magnet. And that froze the MR industry because they said we'd be able to do in vivo chemistry with a 1.5 Tesla magnet. This was featured in IEEE Spectrum, a journal that we're all familiar with. And Paul Bottomley, a friend of ours and certainly Pablo's, was quoted as saying, doctors one day may be able to evaluate heart disease and monitor the results of therapy by chemical analysis. That's kind of the holy grail. And we're still not doing it. We're trying. That was in 1986. We may be able to do it now with high field magnets, but that's been the problem. 1.5 Tesla wasn't really high enough to do this. So now there are 7 Tesla magnets. Here's a beautiful paper with the first whole body imaging at 7T by friend Tommy Vaughn at Minnesota. And you can see the problem here. We get these dark nulls, and these dark nulls were not predictable. They're dependent on the patient size. So how do you mitigate that? Well, it turns out that hardware and software advances in phased array antennas mitigate that. Eliminating the problem is not the objective. That's not really what we're going to try to do. You just have to mitigate it. And this group, tremendous group up in Minnesota, is working hard on that. Here's an example of a recent paper just showing that they can do good hip imaging simply by using phased array transmitters to move those nulls away from problem spots. So it's, in this case, it's all about the hardware. Phased array antennas, high field magnets. Sticking with spectroscopy, just getting a spectra may not be good enough. We actually want to do metabolic studies, in which case we may want to look at changes in spectral signatures with time. Here's an example, just showing an exercise trace of the PCR peak changing with time over a matter of seconds. We want to be able to follow that. That requires high signal to noise, which is going to require phased array antennas. Phased array antennas are complex to build. And then when you add into that the fact that we'd really like to do multiple nuclei at the same time if we're going to do metabolic studies. This is just an example. I won't go into it, but they're studying potassium, sodium, and proton imaging. Each one takes about 30 minutes. That's a long time to have a patient with a magnet. So we'd like to raise the bar. We want to do simultaneous multinuclear imaging spectroscopy. Once again, an idea that's been around almost as long as MRI. And a couple of great groups, Z.H. Cho, who actually gave the first talk I ever heard on MRI, and then Keith Fulborn, who did the first 4 Tesla human MRI. They were talking about this back in the 80s. That's not the right, 1981's the date. Very hard to do back then. You cobble together the systems. Today, this is going to be done with high field magnets. It's going to be done with hyperpolarization, something I won't talk about here. And we're going to need array coils to get the speed that operate at multiple frequencies. That's a very complex problem to do all of that. And it's all about the hardware. All of these applications require and have generated just tremendous research in MR hardware, which fortunately is what we're interested in. Phased array receivers for improved SNR, pretty well done now, but we've done a lot of research on that in our day. Fast imaging techniques, very important for hyperpolarized MRI. It's going to make metabolic studies likely going to be a key for that. Phased array transmitters, cutting edge area of research right now. And then multinuclear arrays, these are huge challenges. Open hardware approaches are becoming very popular for many reasons, one being training. We want to be able to train students to jump in and contribute. We don't have a big program. We don't have 30 people with people constantly streaming in. We throw people like Courtney under the bus, and they have to produce. So we need ways to train them. And that's what we're going to talk about. So let's talk about building a basically open desktop scanner. Here's our first desktop scanner, built in 2002 or published in 2002. It's a little bit complex. There's a lot of hardware stuffed into this box. And this was a 0.22 Tesla magnet. It used National Instruments boards, an analog devices receiver chip. We estimated about 12,500 parts and about 3 times that in student time to put it together. It worked great, but it's not suitable for a lab course. This is just too complex for a lab course. There's the reference for it. It worked great. Here's a little 3D Phantom. And here, hopefully this will run, is a 3D image going through that. There we go. And you see the wire that's been wrapped around those capillary tubes. So that's a little desktop scanner that worked quite well. And it led us to saying, well, we could build a course where students get a chance to build one of these things, but we needed to simplify it. So we developed this course with this platform. So we use this magnet I'll talk about in a minute from Alan Sahakian. We had a chassis of National Instruments cards, interface box, some commercial TR switch, preamplifiers, amplifiers, homemade grading amplifiers, and of course the magnet. And here's an example of the image that came off of this. It's been that way for 10 years. It's projection reconstruction, and the students actually rotate the object. They just physically rotate it to get the different projections. And here's an example. We have a best image contest most years, and these are the images. We let the students do whatever processing they want. Some of the images look pretty good, but some of them are very heavily processed. But they write software in LabVIEW. They build an RF coil. They build one gradient coil, and they obtain images. And the students do learn a lot about debugging because it's not trivial to keep things working. But I wasn't satisfied with those images. We wanted to improve it. And I asked Courtney Bauer, who was the TA for the course, to try to do phase encoding on that platform. And it does direct sampling, so the amount of data that comes through is large. It was questionably phase stable, so all of her images were one average images, but she actually got it working. But we felt that the cost and accessibility issue just wasn't ideal, and it was really too difficult for a 3-hour lab course. So we wanted to revise the course. National Instruments equipment is not readily available to the students. It's just too expensive. They don't have it at home. The software is fantastic. We do have these open lab, the shared lab, but it does require a TA to be present. So the students couldn't go into the lab equipment and get it working. So we wanted to develop an MRI scanner that could be built with just parts off of Amazon, objective number 1, so that the students could test their software at home, make sure it's working before they come into class, which we may have to discuss. And then, of course, we wanted to use this to teach students the fundamentals of MRI. So we looked at a few approaches, sticking with NI. Okay, it's outstanding equipment. Students can download LabVIEW, but without the instruments, they couldn't test their software at home. So they came into the class and had to develop software, had to debug their software. There's an instrument called the Red Pitaya, which is just an excellent instrument. It's a whole lab in a box, highly capable. It's the basis for something called Okra MRI, and the link is there. It's a fantastic system, but it's a bit cumbersome. They programmed through the FPGA, and most of our undergraduates aren't comfortable programming directly in VHDL. And most importantly, our department did not adapt this lab-in-a-box kit for their labs. We could look at doing SDR-based MRI. Will Grissom's group, when he was at Vanderbilt, used software-defined radios, did a fantastic job. There's the reference there. It's a very complete system, but it uses new radio. A bit complicated for an undergrad to learn to use all that. So we decided not to do that. Andy Webb has his OSI, I think that's OSI 2, OSI 1. They label it the first open source MRI scanner, and he's got a great group. Here's the reference. It's a full out imaging system, not really suitable for a teaching system. Many other approaches are out there. Google it. There's lots of desktop scanners, but none as simple as what we really had in mind. So our department adapted for their early lab courses the Digilent Analog Discovery 2. Like the Red Pitaya, it's a lab in a box. It's got oscilloscope, waveform generator, logic analyzers, pattern generators. And all the students have it, and all the students have experience with it. So the learning curve, in principle, should not be as steep. And they've all experienced with Python from their early classes. So we decided this would be a perfect platform if it's capable. So the first step, Jacob Carroll, who's sitting here, and Reed Smoot did a senior design project where they tested out whether or not they could actually use this and get MR images. So they built a little front end. They built a magnet that was designed to replace our 40-pound magnets, a Halbach magnet. And then they tested and were able to get projections off of this magnet. But unfortunately, the line width was not as good as we'd hoped. And so when they went to make images, they went back to a 0.06 Tesla whole body magnet, which had a very good field. And they did make a projection reconstruction image with the 82. So it's a great sign. You know, the 82 should be able to work. All right, so then we went through designing a new system for the course. And here's a block diagram, very simple. Magnet and gradients, course matching network. We need a TR switch. RF comes in from the Analog Discovery 2, and then we have an attenuator so we can switch between 90 and 180. The students have all played with this just this last week. On the receiver, we have a 60 dB gain RF preamp, low pass filter. We have to mix because of the 82's depth of memory, and then a low pass filter, and then right out to the 82. So the Analog Discovery produces our local oscillator in, our RF in, and then digitizes the signals, and it can provide 1 or 2 gradient channels with just one 82. So you can do a lot with just one analog device. So let's talk about those systems. So the magnet, as I said, the Halbach magnet, we're not there yet. Jacob's still working on it. We would hope to be able to use that in the future. So we stuck with a design from Alan Sahakian, the reference is here, which he also introduced as a teaching tool. It's a wonderful design, very, very simple. And here's a picture of his magnet from his publication and a FID and an echo that he got from it. He did that with a couple of 555 timers for pulse control. So here's the prototype of that. We've been using that magnet for 10 years in this lab class, and we're going to stick with it this semester, and hopefully after that move to the Halbach. So here's the prototype showing the RF coil assembly. You can see the gradients here. These are the field spreaders, basically a pole piece. And then down in here are two by 2 by 1 inch neodymium iron boron magnets. So this is very simple. We just plug in, just piece this together, weld some steel around it, you have a magnet. There's what I've called a temperature sensor, which is just a thermometer, because it turns out there's a high degree of temperature variation. And interestingly enough, just last night I figured out that my matching network is also very temperature sensitive. Must be the variable capacitors, because room changes by a degree and I have to retune. Gradient coils unchanged from our 2010 paper, right out of Anderson's classic paper. We get about half a Gauss per centimeter per amp. In previous years, students optimized and built the Z gradient, but I'm sure they'll be happy to know that I think Jacob will be providing them for them this year, just because of time. The gradient amplifier board, we just went out and bought 3 audio amplifiers from Amazon. That's it. A way to change the gain by changing one resistor to lower the gain. There's no volume control on these. Each one is $60 on Amazon. We can source about 5 amps, so we can do about 2.5 Gauss per centimeter. The objective was, if one of them fails, we just put a new one in. We didn't want to build these, wanted to be simple, something any student can buy. All you need is one to be able to do projection reconstruction imaging. So, and I am looking for cheaper solutions. Hopefully we'll make that even cheaper. Here's the RF front end. This is the embodiment of the block diagram. So here's our TR switch, HMC 544 chip. If you Google that, it's 25 bucks on Amazon. Works great. The attenuator is $11 on Amazon, and that's what we switch to go between 90 and 180 pulses. 60 dB RF preamp, 60 decibels, 22 bucks on Amazon. I've replaced that with very expensive Mytech preamps and got about a factor of 2 improvement signal to noise. $22 is fine. We do have a 3.5 megahertz low pass filter in. Wanted that to be band pass so we could do direct sampling, but I didn't have that. This is $19 online at that website. Mixer to mix down, $12 on Amazon. So this very cheap stuff. The most expensive component is this low pass filter, which any electrical engineering student could build for themselves. 77 bucks at Thor Labs. But, wanted to see what we could just do online. The whole thing takes about 12 milliamps. So I've run it off of batteries trying to track down noise. That's why I've got this in here and this indicator, so I know if the batteries are dying. And that's $3 off of Amazon. It would be better shielded, but this is a teaching course. We want you to be able to get in and adjust, things, move things, tap into test points, things like that. So we haven't shielded it. Doesn't seem to be a big problem, he says. We're on the edge of our RF power requirement straight out of the 82. I mean, we can get a 9180, but we don't have a lot of headroom. And it would be nice to put an additional RF amplifier in, but then you need an additional TR switch to mitigate the noise on idle. So we got rid of it. And this does work. The important part is the spectrometer, the control system. So we've got two 82s. One does the RF, and I've got one that's doing the gradients. The RF one, we do use the breakout box, which I think is $20 extra. And then we just come to this board so that we can use fly wires to get at our control signals, because the front end is connected here, and then the students just run wires appropriately. But you have to have a little additional hardware because the 82s are 3.3 volts. The attenuator uses 5-volt logic. So we had to convert that with an inverter chip. This is where the gradients connect, X, Y, and Z. And the fly wires are a poor man's ability to change imaging orientation by just moving around which gradient goes to which physical coil, the X, Y, or Z. So it's very nice. I can switch from sagittal to axial view by just swapping these 3 wires around. This is completely optional. I had that at home and I use it for independent monitoring of the waveforms. So it's not necessary. That's it. The RF coil is a solenoid. It's inside a shield. So the coil sits here. This open shield is a cutoff waveguide, and it gives about 55 dB of attenuation down to the middle of the coil. So it's plenty. And then I can load in samples from the top. Signal comes out the bottom. It's a little cumbersome, but it does work. This goes into the magnet. We build a very broadband matching network, switchable extra capacitors. That lets us match almost any coil you want to build, and you'll all use that in the lab. And that's it. The parts are being assembled now. Jacob has built the matching networks and the gradients. Courtney is building the front ends. I think that's about done for next week. In the labs, they do the transmit front end this week, receive front end next week. Then they'll build an RF coil. They'll obtain a spin echo. They'll learn about gradients and image localization. They'll do projection reconstruction imaging. And then the last couple of weeks is a project, and the students can choose what they'd like to work on. Direct digitization, 3D imaging, diffusion imaging, better RF coils, slice selection, whatever. So system's built now, it's time to test it. And so here's an example. All right, so here we're adjusting the frequency. So you probably can't read this stuff, but it says calibrate equal 1, which means adjust frequency. And if calibrate equal to 1, it turns off the gradients. And when you ping the system, told it to ping it 3 times. First time it's off resonance, then it moves to the resonance and prints out the frequency. You then enter the frequency up here, turn off calibrate, set that equal to 0. We can set our TE, TR, number of averages, field of view, and acquisition rate all through here. And this is why Python's probably going to work better than waveforms, because it's hard to build this kind of flexibility into waveforms. But once you set it up, you can move to imaging. And this is just an example I tried to run last night. I would like to have done it live in class, but I didn't want to bring the magnet down. So let's see. Let's start. Come on. Well, anyway, you run this. It takes about 15 seconds. You see the gradient waveforms in this window, which would have been very nice to see. Oh boy, now it's going nuts. You can edit that off the YouTube version. All right, sorry guys, it's not working. So what you get is this. 15 seconds later, you get a horrible image in this case. I had noise all over my office last night. I don't know why, but it turns out the gradients ran. You saw them in the video that should have run, and amplitudes were right. The field of view, this is a round test tube, is correct. What that means is you've got everything set up. So now you can take more averages, get a better image, but you don't have to waste time waiting for that to come out. In this particular case, the software puts out the real and imaginary, the raw data, the uninterpolated image and the interpolated image. And if you can see it, and it's hard to see, there are noise spikes in the raw data. So something in my home was spiking last night, messing up the images. That's all right. Here's some other examples to go through. So the effective acquisition time. So here's a 25-second calibration image, 15 kilohertz bandwidth, just a test tube with a plastic bolt in the middle. 128 by 32, so very low resolution. Half a second TR, 12 millisecond, 15 kilohertz bandwidth, 8.192 milliseconds acquisition window. If we run more averages, we get a pretty good signal to noise. It's kind of lopsided. Where does that come from? Because it's a test tube. That's the magnetic field image you should deal with. How do you solve that? You increase your gradient strength, so it dominates the magnetic field variation. And okay, we increase the magnetic field strength to increase our bandwidth to 25 kilohertz. We get a much more round image, but the signal to noise went down. If you go up to 50 kilohertz, it's a bit more round, but you've lost more signal to noise. So you have to find your optimum. It's a trade-off. Everything's a trade-off in MRI. We can change contrast. So here's two compartments. This has got distilled water in it. This has got distilled water with 1.1 gram per liter copper sulfate. This is a T1 weighted image, and you don't see the distilled water. And my parameters were bad, so it's low, relatively 15 kilohertz bandwidth. Decrease the resolution because I wanted better signal to noise. Change to a longer TR, mid TE. So this is mixed weighting, and now you see the distilled water and the copper sulfate, same intensity. Here we go to a very long TR, long TE, and now what you see is the distilled water and very little from the copper sulfate. So this is how clinical MRI is done. They want to measure T1 and T2, and you do that by controlling your pulse parameters. What kind of resolution can we get? Well, here's a 10 millimeter test tube with some coffee stirrers inside. And I was hoping the coffee stirrers would, when I put them in, I was hoping that the fluid would get inside them. It only did inside one. Here's a very quick image, but it was, it indicated that things were working. So I ran more averages. You get a pretty good image of the 10 centimeter test tube, that 1 centimeter test tube with some coffee stirrers. So that's a 1.75 centimeter field of view. Reasonable image. Obviously, the final question is, can we do 3D imaging? So I spent most of my weekend trying to make 3D phantoms. I'm not good at that stuff. So I reduced down to just making a little spring of wire, dropping it inside a test tube. And so that was my phantom. And then here's what I got. Oh, come on. Okay. So if I stop it, say here, if I could, back up. Oh, terrible movies. Anyway, we'll play that one more time. You can see the so here are the wires in the spiral cutting through. Here it's actually cutting through two sides of one loop, but it actually works. So that's a 3D image made with an 82, and one that every student has in a handful of parts. So it seems to be working pretty well. Next step is to try to add some more interesting lab exercises with it. All right, so let me go back to the talk. Start with that hiccup, guys. Okay, that was really it. Other than on that desktop, so I'm not going to pull that one back open. Other than to say what's next. Well, what's next? We really want to get the Hallbach magnet working, so that because the Hallbach magnet was made with about, I don't know, $25, $30 worth of magnet material off of Amazon and a 3D former. And so any student can build that very easily. Slice selection would really be good. And maybe shielding the front end, but if you shield the front end, you don't quite have the same access to it. So I'm not sure. All right, real quickly, I won't go through these two, but this is a summary of it. Okay. Yes, it's automatically going through all my slides. So using modern open hardware, easily accessible hardware, we built a streamlined broadband MR scanner. So essentially one 4-channel fast digitizer, high-speed DAC, a combiner. We generated multiple RF pulses through a broadband TR switch into a multi-tuned coil, and then got signals from multiple samples at the same time. There's a picture of the system built in the lab. Here are the parts that went into it. I'm going to hurry through this just in the interest of time. Here's simultaneous, truly simultaneous. So this one RF pulse excites both proton and deuterium, and then the echo comes back from both. And this is a phantom with decreasing concentrations of one and increasing of the other. And that's what we get. Obviously, the resolution for 2H is lower. And then we repeated this with a different coil, simultaneously proton, sodium, and deuterium, just to show the flexibility of the scanner. So these are all obtained at the same time. And the signal to noise comparison was actually very good. We lost a little on hydrogen because our digitizer was not quite high enough frequency to sample that. We'd undersample. But the other ones we actually did better. So in the remaining 2 minutes, let me just summarize that if you want to do multinuclear, simultaneous spectroscopy, you're going to need array coils. And array coils are complex enough alone. And what people do is if they want to do multinuclei, they essentially take two arrays in general and just stack them on top of each other. There are some cases where they've double tuned the elements. And there's cases where they've used pin diodes to switch frequency between scans. But this introduces significant complexity. So what we wanted to try was making a broadband array coil. And that's in this paper here. Just came out in MRM from Chen Hao, but here's the array, a 4-channel array. These preamplifiers are high impedance. We essentially match to them using a transformer. So the transformer provides a broadband impedance match. And we built a phantom with deuterium, sodium, and proton, different concentrations, and then used the same array, no tuning at all, just the same array at these 3 different frequencies, and made array images at all of them and I'm hurrying through this, but signal noise, there's a little signal to noise loss. Less at sodium than at deuterium, but it's pretty good comparing to a conventional isolation preamp where you would have to have separate preamps for different frequencies. This is just the same preamp working at the same frequencies. So just on a lark, we decided to take the same coil over to a 3T scanner. So a 4.7T coil, we just took it to a 3T scanner, built another phantom with phosphorus, sodium, and proton. And then we stuck it in the same coil and we made images. These were CSI images of sodium and phosphorus on a 3T magnet. Didn't tune the coil at all. We lost one element for some reason. We're not exactly sure what happened. And we have to pay for that magnet. We don't have to pay for ours. So we haven't gone back to use that. But the point is now we've tested the single coil at 5 different frequencies on 2 different magnets without retuning. And we think that's kind of useful. So the wideband electronics, we can now really do truly simultaneous or interleaved MRI, multiple nuclei. High impedance preamplifiers allow broadband decoupling. That's the challenge, is decoupling those elements so they work independently. So we're pretty happy with that. All right, so finally, and then maybe there's some questions, conclusions. New hardware really allows us to simplify MRI, eliminate more and more of the electronics, go more and more digital. We can do broadband MRI, and so we can now operate RF coils over multiple nuclear with little or no tuning. And I think most importantly, we've demonstrated a full 3D capable MRI scanner that any student can build with a handful of parts and 2 Analog Discovery 82s, which are issued to all the students in our program. We need to get the magnet cheaper, and we're working on that. But it's a great tool for training students in MRI. So I'd like to thank Pablo and the LIBREhub team for inviting me to speak. I really appreciate it. I apologize for the snafu on the videos. I did test those. They did work. So something about Zoom and those videos that didn't like each other. Lots of people participated in this work over the years, particularly Mary McDougall, who worked on developing the initial version of the course with me. Current PhD students, Courtney, Ryan, and Madhavan helped with the broadband stuff and the desktop scanner. And then, of course, Jacob and Reed, who did the initial testing. We appreciate that. And our support from the NIH. With that, I thank you, and I'll open it up if there are any questions. Thank you very much for the invitation. I really appreciate it.
Thank you so much, Steve. We enjoy your talk, and hopefully we'll keep in touch, and we'll have a lot of things to share, I think.
Good. I look forward to it. Thank you, everyone.